Today we will see how some of those matrices can be made to work for us. So, slowly we are moving towards application, and while we do that we will also integrate this with something that we learned from group theory. So, before learning anything new, let us recall what we closed our discussion on group theory with previously and what we have learned so far in matrices. So, this I think everybody remembers now, similarity transformation. Similarity transformation is B equal to x inverse A x, where A, B, x all have to be elements of the group, okay, of the group, not the subgroup, not the class, alright. A and B are called conjugates, and a class is defined as a complete set of elements that are conjugate to each other. So, I hope you know this already. Any chemical example of class that we discussed? An example from chemistry of class? From symmetry? C? C3 and C3 square in C3V belong to the same class, and sigma V, the 3 sigma V's belong to another class, and that, as we saw in the previous day, conforms very nicely with the G6-2 kind of multiplication table that we had used, okay. So, everything falls in place so far, fine. So, how did we define the members of class so far? First of all, they have to be similarity transformations of each other. Secondly, I am talking about symmetry operations now, symmetry operations in the same class. We discussed 3 ways of defining them. First is that they have to be similarity transformations of each other. Yeah, they should be transformable into each other by an operation outside the class. And what was the third property that we discussed? Character should be the same. So, let us see today if we can have a more formal discussion of why the character should be the same, right. What we have done so far is that we have only demonstrated, right. We have taken a matrix, we have taken 2 matrices Cn plus and Cn minus, and we have shown that the characters turn out to be the same in these 2 cases. Today let us see if we have a more general derivation of this fact, alright. And then what are we doing is, we are approaching the problem. I do not know what has happened, these are supposed to be all invisible anyway, I think I goofed up. So, anyway, so we are going to do this, the tool of trade that we are going to use is matrices. As we saw earlier, the symmetry operations can all be represented as matrices, and we have had a glimpse of how you can block factorize these matrices even manually and generate what are called representations. What are representations? But what is the definition of a representation? When I say representation, what do I mean? So, a representation is basically a collection of numbers or matrices, okay, spanning over the entire range of symmetry operations for a symmetry point group, okay. And representations arise, so far we have seen that we have used different bases, as he was saying. For water we had used oxygen, hydrogen A, hydrogen B, or we also used X, Y, Z, different bases sets if you want to call them, and we have seen how they get transformed with respect to each and every symmetry operation, and then we took a collection of those for all the symmetry operations. That collection was called a representation. So, representation is of a symmetry species, of something which has a unique set of behavior with respect to all the symmetry operations that are there in a particular point group, right. So, that is a representation, all the symmetry operations taken together. What are the matrices or what are the numbers? That tells you about a particular kind of behavior, right. We will come back to that when we talk about reducible representation and irreducible representation once again. But before that, we will need to know more about matrices, and this is what we discussed in the previous class. Everybody knows what a diagonal matrix is. I think everybody knows what a real matrix is. In very simple terms, a real matrix is a matrix in which all the terms in which none of the terms are imaginary, let me put it this way. If I say all the terms are real in real matrix, that also sounds very funny, isn't it? Incidentally, I saw this cartoon somewhere where I and pi are giving each other a hard time. Nishit has seen this. What does I tell pi? Be rational. And what does pi tell I? Get real. I is imaginary, right? I for imaginary. And what is the value of pi? By the way, we are digressing a little bit, but this is useful. What is pi? Pi equal to? Okay, if you did not say approximately, you would have got a 0. Pi is not 22 by 7. Pi is an irrational number, don't forget. If pi is 22 by 7, then it becomes a rational number. So it is 3.142, then I don't remember after that. But it is an irrational number, there is no end, it goes on. What is pi? How is pi defined originally? Experimentally, pi is an experimental quantity. Yeah. Circumference equal to 2 pi r or pi d, right? So pi is basically circumference divided by diameter. But if your diameter is exactly 7.0, your perimeter, your circumference will never be exactly 22. It will be a little more or little less, right? So it is not 22 by 7. Fine. Let us come back to what we are talking about. So real matrix, the more formal definition is Aij equal to Aij star for all values of I and j, right? And then we talked about transpose and adjoint or Hermitian conjugate. Transpose is very easy, just interchange the rows and columns, right? So essentially you give a 180-degree twist with respect to the diagonal. Since the class in symmetry, you might understand it better this way. You take the diagonal, that is your C2 axis, you turn the elements by 180 degrees. Okay. What you get is a transpose. Interchange the rows and columns, and it is called either A dashed or A tilde. I do not know whether it is really called A tilde, I call it A tilde, I do not know if it has a more proper name. And what is an adjoint or Hermitian conjugate? A dagger. A dagger is A dash star. That means not only do you transpose, you also take the complex conjugate of each and every element, alright. And then symmetric matrix is something which is equal to its transpose, A equal to A tilde. That means in that case that C2 operation along the diagonal is a symmetry operation for those matrices, isn't it, right. So here we had worked out, we had given you a matrix A and you had worked out what is A dagger, remember. And then we talked about Hermitian matrix. What is a Hermitian matrix? Hermitian matrix is one in which A is equal to A dagger, please do not forget these two. In Hermitian, A equal to A dagger, and in unitary matrix, this is the only place where the cover has worked, A dagger equal to A inverse. So if A dagger equal to A, then A is Hermitian. If A dagger equal to A inverse, then it is unitary. Okay. Another way of putting it is that A dagger equal to E. And here we had given an example of Hermitian matrix also, alright. So what is Hermitian? A equal to A dagger. Transpose it and take complex conjugate of each and every element. The matrix that you get is, if it is equal to the matrix that you started with, then A equal to A dagger, Hermitian. And what is orthogonal matrix? Orthogonal matrix is one in which A transpose is equal to A inverse. A transpose equal to A inverse. That is going to work for real matrices, right. So do we all know these definitions? We are going to use them regularly in the subsequent discussions. So if you do not know what unitary is, this is your last chance to remember, right. And then this is where we had stopped. What we had done is we had taken a matrix, a general matrix, and then you had worked out A dagger for it, and then we said let us say that this is a unitary matrix. So, if it is a unitary matrix, then A dagger should be equal to E. So, what you have done is you have worked out the 1 1 element and the 1 2 element. 1 1 element would be 1 in unit matrix, 1 2 element or 2 1 element for that matter would be 0, and this is what you got, right. You got A11 into A11 star plus A12 into A12 star plus etc., plus A1n star equal to 1. And you had also got for the 1 2 element A11 A21 star plus A12 A22 star plus etc., plus A1n A2n star equal to 0, right. So, welcome back Sumit, I was worried that you have left us. So, see these matrix element then behave like a set of orthonormal vectors, right. You multiply an element by the complex conjugate of itself and then add up all the products that you get 1, and then multiply an element by the complex conjugate of something else and add up all whatever you have, then you get 0. So, that is the property of a set of orthonormal vectors, and in quantum physics, quantum chemistry, you encounter these orthonormal vectors all the time, right. They come back to haunt you everywhere, right. That is why these unitary matrices are so useful. Anybody who works in quantum mechanics or quantum chemistry actually loves unitary matrices because you use it all the time. Okay. So, this is where we had stopped, this is where we will start today. Now, I had asked you to try and write down the general expression. I have invoked k as well, right. So, sum over k equal to 1 to n A I k A j k star equal to del I j. It is a little easier to write if you invoke k, right. Okay. What is delta I j? Is Kronecker delta. So, when these are same, then it is 1, when they are different, then it is 0, that is all. What is 0? Is each element 0? Then the sum of the products is 0, do not forget that please. The sum of the products is 1 if you are multiplying each element by complex conjugate of itself, sum of products is 0 if you are multiplying the complex conjugate of anything else with an element. It does not imply in any way that each and every vector is 0, please do not have that confusion. You have to invoke k, otherwise it is very difficult to write. Okay. Now, let us move on. Here are two examples, one of a unitary matrix and one of an orthogonal matrix. Okay. But of course, just because I say that this is unitary and that is orthogonal, there is no reason why you should believe me, right. I think Max Planck had said experimental results are the only truth, everything else is poetry and imagination, right. So, now work out the adjoints and prove to yourself that this is unitary and the second one is orthogonal. Let us start with the first one. What is the adjoint of the first one? Everybody knows what omega and omega square are, right. What are they? Cube root of 1. And how is omega related to I? Is omega related to I in some way? It is not related to I at all? Homework problem number 0. Homework problem number 0, find out relationship between among omega, omega square and I. Is there a relation or is there no relation? I mean omega and I, omega square will follow. Is omega in some way related to I or not? Well, if it is not, then you are going to have another number line, is not it? You have a real number line, and then when you multiply by I, what happens is that you get a perpendicular imaginary number line. So, if you need another number line in omega, then we got a problem, right. And omega square definitely cannot be real, because if they are real, then they have to be 1, right. So, they would better be related to I in some way or the other. Please find out how they are related to I, fine. But let us move ahead anyway. What is the complex conjugate of omega? So, Avinash, tell me what is the complex conjugate of omega? Omega square. Very good. So now work out the adjoint. First one 1 0 0, that is the first row. What is the second row? What is the second row? 0 0 omega square is just the transpose. I want the adjoint. 0 0 omega. What is the third line? 0 omega square 1. Right? Is this right? 1 0 0 0 0 omega 0 omega square 1. Have you seen this matrix somewhere? Have you seen this matrix somewhere? Yeah, you have seen the matrix right here on the same page. Same matrix. So, what is it? A equal to A dagger, right? If A equal to A dagger, what kind of a matrix is it? Dalmatian. What? Hermitian matrix. Speak loudly and clearly. Do not be scared. If you say anything wrong, we will just edit it out. Don't worry. It's a Hermitian matrix, right? Is it also unitary? Multiply and see. What is the condition for a matrix to be unitary? A into A dagger equal to 1. You know A, you know A dagger. So multiply them together and see what you get. We have already established that this is a Hermitian matrix. Are likho na re baba. What is the point of saving so much of paper? Multiply them together, what do you get? So it is a typing mistake. Last one has to be 0. 3 element, if it is 0, if it is 0 then it works out, right? So I have to change that. Now, but then the point is it still a Hermitian matrix? It's Hermitian and it is also your unitary, right? Right? If it is 0, the last one is not 1. This has to be 0. So this is just once again perils of copy paste. Alright, Hermitian as well as unitary. So what we learn is that there is no problem for a Hermitian matrix to be unitary. They are not mutually exclusive. And also what are we getting here? We take a matrix, multiply it by itself and get unit matrix. Such matrices have another name. A square equal to 1. What is that called? Is it also A square? No, it is not A square equal to 1. Is it A square equal? Yeah, it is. It is. A square equal to 1. So, if A square equal to 1, what is such a matrix called? Idempotent. That is right. Idempotent. And if it is 0, nullpotent. So, see, this one matrix is so many things. It is an all-rounder matrix, right? Which reminds me, can a process be isothermal as well as adiabatic, like this matrix? We know of isothermal expansion, we know of adiabatic expansion. Is it possible to have a process that is isothermal as well as adiabatic? Free expansion is isothermal as well as adiabatic. Rejazer is not reversible. Okay, let us move on. Instead of going off orthogonally to our discussion into thermodynamics and all, let us rather talk about orthogonal matrix. B, what is the transpose of B, and hoping that there is no further typo here. What is the transpose of B? Cos theta minus sin theta 0, sin theta cos theta 0, 0 0 1, right? Can you multiply them together and see what you get? Multiply them together and see what you get. B multiplied by B transpose. what do we get? Do we get the unit matrix? So, if we get the unit matrix, is it an orthogonal matrix? Yeah. Okay. So, here we have taken two examples, there was a little mistake in the first one, but then that is not such a big deal. Maybe I will correct it here before I forget. Now it is okay. Yes, sir. Yes. Yes. That is right. Yeah. X, Y, Z with X, Y, Z as the basis. That is right. Rotation by theta plus and minus. Fine. So they are orthogonal. Okay. Fine. Next. I think this is something we have studied in matrix, whatever matrix algebra we have done. So, I am not going to spend 20 minutes deriving it actually. Please read it by yourself just to remind yourself how it came, but I think this relationship is not very unfamiliar. How do you get an inverse of a matrix? What is the inverse of a matrix? What is the definition? A inverse of a matrix is a matrix which when multiplying with itself gives you E, okay, and they commute with each other, fine. So, this is inverse 1 by determinant of A outside, and then what is this matrix called? What are all these stylish A's? Cofactors. Cofactor is there in biology. Where did cofactor come from in matrix? There is a cofactor in biology, right? Enzyme cofactor, cofactor is there. So, what is this mathematical cofactor? How is cofactor defined? Come on. What is cofactor? When I say A11, stylish A11, what do I mean? Yeah, okay, right. Take out A, take out the first row, take out the first column, whatever is there, make a determinant of it. That is cofactor. And what about sign? Right. So, det A is the determinant of A and these stylish A's are the cofactors of the matrix elements, alright. Now, where do you use an inverse? All of a sudden, why have we started talking about inverse? The biggest use of the inverse of a matrix, right, is in simultaneous linear equations. I think we all know that we can write a set of simultaneous linear equations in the matrix form. We have already written one or two already, right. This is general form A11, A12 etc. up to A1n, and then the column goes A11, A21 all the way up to A11, N1, and then you can fill in all the n by n elements. So, when this matrix operates on x1, x2 etc. up to xn, then you get y1, y2 etc. up to yn. I hope you are all familiar with this, right. Can you write the equations actually? What will be the first equation here? A11 x1 plus A12 x2 plus 1 and so forth. Last is plus A1n xn is equal to y1 plus y2 plus y3. No, only y1. Only y1. Okay, good. So, in that case, what is y1? A linear combination of the x1s, or if I may put it that way, it is a mixture of the x1s, right? Right? Yeah, of course, whenever I say a mixture, you think of wave function, that is right. Fine. So, now Ax equal to y, if you left multiply both sides by A inverse, what will happen? On the left hand side, you will get E, the unit matrix, and you get x equal to A inverse y, right. That is how you work it out, and we already know what A inverse is. Okay. Is it so are we saying that every square matrix that is there, we restrict ourselves to square matrices, every square matrix that is there that I can write, is it going to have an inverse? So what is the condition for having an inverse? This, right? If it is 0, then you got a problem. So the essential condition to be able to invert a matrix is that the determinant should not be equal to 0, right? I think we know this. Determinant should not be equal to 0. If the determinant of a square matrix is equal to 0, then it is a weird matrix, it is a weirdo, right? It is a renegade, outlaw. But since we do not want to use such impolite terms, we use a polite term and call it a singular matrix. If the determinant is equal to 0, then it is called a singular matrix. What is the meaning of singular? You can actually guess even if you do not know. Singular, one of a kind, but one of a kind in not such a positive sense. Have you guys read Sherlock Holmes stories in original, in English, right? Sherlock Holmes keeps saying all the time, isn't it, Watson, I see a singularity. Singularity was a very pet word of Sherlock Holmes, or the writer of Sherlock Holmes rather. Singularity, singularity means something that stands out, exceptional, okay. So these are exceptional matrices, singular matrices, problematic matrices, okay. There is another more formal definition of singularity, right? It has got to do with a breach in space time, that is also called a singularity in astrophysics. But here singular just means a matrix that cannot be inverted, and the reason why it is called singular is that it is weird, it stands out, it is not regular, right, an outlaw, Phulan Devi kind of matrix, okay. Now, so we have talked about simultaneous linear equations. Now, one particular kind of simultaneous linear equations that keep occurring in quantum mechanics is called the matrix eigenvalue equation.